All right. Welcome back to the session. Next, we have Professor Azita Emami, the Peggy and Andrew Cheng, Professor of Medical Engineering and Electrical Engineering, who's going to be giving a talk on intelligent devices for brain and body interfaces. So, welcome, Azita.
Thank you, Yang. Hi again, everyone. So in my group, we are excited and interested about building miniaturized medical devices that can perform sensing, recording, and stimulation. And today I would like to talk to you how we can take a co-design approach between hardware and software and also embed AI in medical devices to improve their performance. So I will talk about two projects. The brain-machine interface project in collaboration with Professor Richard Anderson at Caltech, who is a neuroscientist, and heart monitoring and arrhythmia detection in collaboration with Professor Anand Kumar, as she briefly mentioned. So let's start with brain interfaces or neural interfaces. They have been around for over 2 decades, and some of them are quite advanced now and are commercialized. For instance, deep brain stimulation for Parkinson's disease has helped patients with tremor reduction. We also started in this domain first by looking at epilepsy detection and prediction of seizure before the seizure actually happens using machine learning algorithms. And that project led us to this new collaboration with Professor Richard Anderson on brain-machine interfaces. So in this kind of systems, we normally have electrode arrays implanted in patients who have a spinal cord injury and they cannot move their limbs or their hands. And the idea here is to record the neural data from specific regions of the brain and then perform prediction on their intention, whether they want to move their hands or move a cursor on the screen. We build systems that can use this neural recording to perform this kind of predictions. And so Professor Anderson has been working in this domain for many, many years, and he has pioneered this kind of brain-machine interfaces. And there are human patient participants that in collaboration with USC neurosurgical department, we implant these Utah arrays that are penetrating electrodes into the cortex in specific regions of the brain to predict intention and movement for subjects. I have to say that then we test the system with quite simple tasks first. The simplest task is called the center-out task, where the patient intends or imagines moving a cursor from the middle of the screen to random points that light up on the screen by thinking. And that's how we evaluate the performance of these systems as a simple task. And then we move on to more sophisticated tasks. So some of you may have seen similar videos like this. These devices now have remarkable performance to some degree, at least in each session. So here, Eric, one of the early participants, moves a robotic arm that follows a red square on the screen that moves randomly. So this is very impressive and remarkable. But at the same time, you see this is a device that can be only used in the clinic and in the lab. And for every single session, they need to perform training at the beginning of the session to get to the point that you see on that video. So a lot of things that before that is happening to tweak things is not shown. So our goal in this collaboration, first of all, has been to first of all improve the performance of these systems and increase their reliability, and also shrink everything into an implantable or a wearable device. So right now you see there are these amplifiers, big amplifiers get connected with a wire, goes to a BlackRock system that does digitization, And then it goes to another computer that does the computing to predict the intention. So we are very far from everyday use for these devices, and our goal is to change the paradigm and make it a usable device for everyday use. So if you look at the brain-machine interface architecture, first of all, the first time you look at the data, it's horrifying because it looks like noise. It's a huge amount of data, very noisy, very small level of voltages that you need to decipher, but a lot of information is hidden in this noisy data. So a lot of pre-processing and filtering is happening. Then there is a module usually feature extraction that I will explain more very soon. And then it goes to a decoder or a classifier that helps us know or predict what the patient wants to do, either controlling a cursor, move a robotic arm, or control the wheelchair. So there are a lot of challenges with existing systems. Right now, a lot of the conventional BMI use spikes as features. This is the firing of the neurons, and I will explain this more. And then usually they use a Kalman filter or a variation of a Kalman filter to perform estimate and find the estimated kinematics. There are a lot of challenges involved. We have non-stationary conditions. This is one of the biggest problems. So every day the patient comes in, some electrodes are working very well, another electrode is not working well because there are micro movements in the brain. Brain is a very dynamic organ. So we will see a lot of non-stationary effects. We have latency in the loop because we have to do all of these processings and we have to go from one module to another module. There are noise and model insufficiency errors. And of course, as I mentioned, hardware complexity and the fact that these systems are very bulky right now. So we started by looking whether we can replace this Kalman filter kind of prediction with neural networks. And recurrent neural networks have been very successful in similar tasks because there is history in neural movement and in kinematics. So we started with a recurrent neural network, but we realized that we can use domain knowledge and understanding of the kinematics of movement and brain activity to create a better neural network that is fitted more for these neural applications. So my student Ben, who is here in this audience, came up with this new type of neural network, which is variation of a recurrent neural network. We call it deep multi-state dynamic recurrent neural network that uses the domain knowledge. It adds higher order the state derivatives to track dynamics of the system. We have movement feedback. And we use neural data history, and we created a deep version of this DRNN to see if we can achieve better performance for this kind of BMI systems. And it was, in fact, remarkable, the results that we got, replacing a simple Kalman filter or even a simple RNN with this dynamic recurrent neural network. So here we define a correlation coefficient, which relates what we predict with the actual intention of the patient. And as you can see, DRNN in offline analysis is performing very well, much better than the other algorithms. And even in online, when the patient is actually using the algorithm, we still perform much better than Kalman filter and other approaches. So this was very encouraging, and we also noticed that we can implement this in hardware because we have tried to reduce the complexity of the system and the amount of memory and number of parameters that we need for these networks. So let me also tell you a little bit about other components in this BMI. So another important building block here is this feature extraction. So in conventional systems, again, what happens is that you have an electrode that listens to the neurons. So you have the option the simplest way to do this is to listen to the neurons that are closest to the electrode. And that's when you can see the spikes. And you can separate these spikes from everything else that looks like noise and then perform threshold crossing to see when the neurons are actually firing. And then a feature would be to take a bin of time, for instance, 50 milliseconds of time, and count how many firing you have, and we call that firing rate and spike sorting here. So this is very good, very simple, because we are listening to single neurons and we are counting the spikes. But at the same time, this is where the problem comes from, that with a slight movement of this electrode, you may not be listening to this neuron tomorrow. You might be listening to another neuron, or maybe no neuron at all. And also over time, we have noticed that because of degradation of the electrodes and separation of neurons from the electrodes, the performance degrades severely after 3 to 5 years, and some of these patients need to be explanted. So now the idea is that what can we do to improve and get more information from the electrodes that are implanted in the brain and actually maximize the amount of information? So let's look back at this. So instead of looking at the couple of neurons that are very close to the electrodes, if you look at the neighboring electrodes, we call this multi-unit activity. It doesn't look like spikes anymore, but there are a lot of information is still there from the neighboring neurons. But we can go even one step further, and basically look at broadband recording that looks at everything that we can around the electrode. Even though they look like noise, but still they carry a lot of information from all the other neurons. So this has been our goal, to create a feature or define features that carry the most information and also help us extend the lifetime of these electrodes in the brain and still be able to decode the information. So that's why we started looking into this automated feature engineering or automated feature generation engines that are best fitted for these broadband signals, and we use learning-based algorithm to generate the features. And we are assuming that the actual process that generates these features are all the same for the electrodes. So we don't want to because we have hundreds of electrodes, we don't want to generate a different type of feature for each electrode. So what we do, which is also different, is that we use the same feature engineering engine for all the channels, assuming that the generative process is the same. So that's what we did very recently. So we have built this FENET, which is a feature engineering engine that involves learning algorithms that generates the features for us. So we have multi-layers of feature generation, and each feature engineering module includes convolutional networks that are trained over a large set of data that Professor Anderson's group has collected over many years. So we trained the algorithm and the offline data that we had. Then we fixed the parameters. We are not going to change the parameters anymore for each session. And we basically generate these features. We do dimensionality reduction to reduce the number of parameters. And then we send it to decoder, which can be a neural network again. So this has been amazing. This patient here, JJ, had the implant for quite some time. And the performance was dropping, and they were about to explant the implant because it wasn't as much useful anymore. And here is where we are. This is a double-blind experiment. The patient doesn't know which algorithm we are using, and the technician also doesn't know which algorithm we are using. And this is a test of a central task that I showed you before. So here, by thinking, James is moving a cursor from the middle to random points or the points that are light up. So as you can see, it's smooth, it goes back and forth. Now we move to, this is the next algorithm. As you can see, it's not as smooth, and basically here we show the trajectory of the two algorithms. This is with threshold crossing, where we are using spikes as our information. And here is when we train the algorithm to extract the best feature from the data. And we show, as you can see, this is an overlay of the trajectories. We show that we significantly improve the performance of this device. And we have had now the patient testing it with grids and other more complex tasks. And he's very happy. He's much happier now with the implant. And he has decided not to be explanted and continue using this device. So this is exciting for us. Our next step is now to implement this on a tiny chip. And another student of mine, Steven here, he is implementing this algorithm on a 65 nanometer CMOS chip to create maybe a 2 millimeter by 2 millimeter chip that will replace a lot of the hardware that nowadays is being used by a big computer. So this is a critical step towards creating an implantable device. So I don't know how much time I have, maybe a couple of minutes.
You have 5 more minutes.
Oh, perfect. So with this time remaining, I want to also tell you about another project where we use AI algorithms to enhance the performance of medical devices. As you know, heart disease is a major problem in the US, and we have millions of people suffering from heart disease, and billions of dollars are spent for treating people with heart problems. One major problem is arrhythmia, which is the abnormal heart rhythm. Some arrhythmia are completely benign, and some of them can be very fatal, can happen suddenly. Some are, if you have them over and over a long period, can be problematic. So the issue with arrhythmia is that some of them are intermittent, and the frequency of occurrence is not very high. And it can be easily missed if you just go and take an ECG in a clinic. It may not happen at that time. So it is actually very attractive to have a continuous monitoring technique for patients who are at high risk, to maybe monitor them even for 1 week and see if arrhythmia is happening or not. So that means that we need to have a wearable device that has very high accuracy. It's a small, light, and easy to wear. It also has long battery life because people don't want to change things or charge the battery. It has been shown that the compliance goes down significantly if you need to charge something or remove a patch and put it back in. So, of course, it should be very accurate, as I mentioned, and it should adapt to the patient's baseline. So that's why we decided to create an on-chip neural network that would be very energy efficient and very accurate so that the patient can wear it and we can detect arrhythmia and classify different types of arrhythmia, the ones that are benign from the ones that are more dangerous. To achieve very low power consumption, we decided to take an analog approach. Everybody does these things in digital for good reasons. If you can do it in digital, you should do it in digital because it's very easy to design, verify, and optimize. But at the same time, it can have high dynamic power because you're swinging all the way to the highest voltage in your system. So we started looking at analog processing because potentially we can remove the ADC. We just send the analog signal into the chip like a wave that travels through the processing units and perform classification. So potentially we can reduce the power consumption and we can use low swing signaling and reduce power. And as Anima mentioned, another interesting thing that we can do is to use the noise as a benefit. Because when we have weights in our system, the weights, instead of being fixed, they are actually, the analog weights in your neural network are actually wiggling a little bit. So you are not fixing the weights in exact value, and that can sometimes actually improve your performance when you have a deep neural network. So we are modeling the noise in our system when we build this analog chip. So we have built this neural network with this relatively compact neural network. Instead of having tens of thousands of parameters, we have only 330 parameters, and you see it's not a very deep neural network, but it has multiple layers. And we have performed a lot of hardware-software co-design by modeling the analog components in actual software to optimize this. And we recently built this chip. It's a very small chip with less than 70 microwatts of power. And we sent the available open source neural heart data to this chip. And we showed that we can achieve very good results with this tiny chip that is not very large network, but has been actually trained by a larger network. I am not going through all the details, but we have used techniques to improve the performance of this system. And we achieved more than 90% accuracy in terms of classification of different arrhythmia or abnormalities. So with that, I want to kind of finish by saying that we can use learning algorithms and hardware-software co-design to significantly improve the performance of medical devices and reduce power consumption towards wearable and implantable systems. At the end, I would like to thank all my collaborators as well as members of my group, and would be happy to answer any questions you may have. Thank you.
So I think we have time for a couple questions. Questions, anybody? Go ahead.
Yeah, where along that arrhythmia path do you go from analog to digital?
I'm sorry?
You were talking about checking those arrhythmias, and you took an analog signal, but where did it get converted to digital?
Oh, that's a great question. So the output of the system is a very, so at the end, we get analog voltages. We get 4 or 5 different analog voltages that indicate each of the classes. And that can go to a very simple ADC. Right now, we don't include that ADC, but it's very low power because we just need to separate 4 levels. And also, it's going to be relatively low speed, so it will have less than a microwatt of power. So at the very, very end, you can actually separate analog voltage level with classes, that whether this is, so we have been using the standard classifications that are available in public data. Good question.
Yeah, in the FENET algorithm for the paraplegic neural brain interface, do you still need to calibrate at every session? Because the results look great, but if you have to calibrate every time, maybe that's not as permanent.
So the FENET, we don't touch it. I didn't have time to discuss this. The FENET parameters, we don't touch it, and it's remarkable. We actually trained it on one patient and tested without touching the parameters on another patient. Because I believe this is looking at the core of neural activity and relationship between neural data and kinematics. And it's similar to spike sorting. Once you do spike sorting, you don't touch it. And that was our idea, actually, not to touch it anymore. And just put this, train it on several patients, and now you can use it on other patients and also for other regions of the brain. So this paper is under second revision by Nature Biomedical Engineering, and we show all the data that how this performs, extends, and is generalizable to different regions of the brain even.
Thank you, Azita, for the excellent talk.